Okay, now we continue with the estimation of difference between two means. This is also rather interesting because it's a very important issue in experimental design. We try to compare the experimental and control groups in a scientific way. So for that purpose, we need to take random samples from two different populations, two different groups. For example, from the experimental group and the control group. And if we want to show this, like suppose that we have two populations, namely population 1 and population 2. These can be experimental and control groups too. So it has its population parameters, 𝐵1, sigma 1 square, and N1, for example. So population 2 has its own parameters as well, like and then you take samples from this population, M1 samples particularly from population 1 and N2 samples from population 2, resulting in some estimators, right, for that population variables, as we discussed before in our previous sessions. So you will have S2 square here. That's the idea. These are coming from the samples. And what we're curious about is the estimation of difference between two means. So what we're seeking is 𝐵1 minus 𝐵2 here. So this will correspond to, or it will be estimated best with this x1 minus x2. So we can say that this one is the estimator, right? Like in our archer and bow analogy, this is the bow, right? In that sense. So this is the estimator, of 𝐵1 minus 𝐵2. It comes from the definition. All right. So the expected value of this is 𝐵1 minus 𝐵2. And when we talk about the variance here of, again, this difference between two means, we can write this like sigma 1 square over n. Okay, this sigma square over n was just for only one of them, right? We have seen this before. Now you add them up. That's it. Add them up. Although it's a difference, we still add them up because it's increasing the variance just like this in this manner, of course, N1 and N2 here. Because why? Because suppose that you're curious about variance of x1 plus x2. Here it's variance of x1 plus variance of x2 here, and like you're curious about x plus x here, 2 variance of x, for example, and variance of x1 minus x2. Okay, not surprisingly, it will be addition again, because variance of x1 plus variance of minus x2. This has been in the theory it's like this. So it's again directly the addition of those variances. That's the idea. And if your N1 and N2 are sufficiently high as well, like if your N1 and N2 are sufficiently high such that, for example, they're both over 30, for example, then this difference, x1 minus x2, then if these are sufficiently high, then x1 minus x2 estimator shows normal distribution. Estimator shows normal distribution. We can assume like this, or we can take it like this. So we can say that if this is the case, then this estimator is also unbiased, and also have minimum variance, right? Minimum variance coming from the definition as well. So for point estimation, what we're trying to do here, or if we want to have the standard deviation here, we just take the square root of that variance of difference here, and if we can use this one. This is used especially when your N1 and N2 are higher than 30. If you have sufficient samples, you can write that like this. And if there is no knowledge about sigma 1 or sigma 2, look at this. These are population parameters, right? If you don't know them, then you can also rely on S1 square and S2 square as well, which these are in fact sample parameters, but we can use them instead of population parameters if we don't have our population parameters. All right, now let's try to solve an example to make it more clear. Suppose that you have two tire production facilities. This is an example from our textbook. Tire production facilities. You can see this example in your textbook as well. So we're talking about two factories here, and we take 100 samples from both of the factories and test their performance. So the first one, the idea is comparing the quality of both brands. We need to compare them. So we're curious about the difference between them, right? The first ones, sample statistics shows that by average they go for this much of kilometers without any problems, and it has this sample set has a variance of this much. All right, and the second factory has some statistic like this. It goes up to more than 25,000 kilometers without any problems. And again, as to of course this is sample average, okay, sample arithmetic mean, and its variance is this much. You know how to calculate them, right? We discussed this in chapter 1. You can either do it by hand, but if you have, of course, this much of samples, it's obvious that you need to have an algorithmic approach for this, or computer-aided support for this. So we're trying to estimate the difference, estimation of mu1 minus mu2 here. So you can use this one, x1 minus x2, for an unbiased estimator, right? It is minus, you already have these values, and it is this much of difference. And what about the standard error here, like your variance, your sigma x1 x2 square should be equal to sigma 1 square over n1 plus sigma 2 square over n2, all right? Of course, assume that where your n1 and n2 are larger than 30. Don't worry, this is the case here. We have 100 samples for each of them, so we can assume it like this. And but we don't have the population parameters here. Again, don't worry, just rely on the sample statistics here. All right, and what you have here will be, it should be equal to S1 square over N1 plus S2 square over N2 here, and the result will be, we already have these values, right? Plus this much over 100 samples for both, and the result will be 34,000. So this is your variance, and the standard error of difference is, the standard error of difference would be the square root of this value, namely take the square root, and the result would be 184 kilometers. This is your standard error of difference. So your interval becomes, if you use Chebyshev here, you go ahead and do this for 75% range, like two standard errors here. So error interval becomes 2 times 184 here. This would be this much of your, it would be your error range for 75% coverage here. We discussed this in the previous session. But if we're trying to use our standard table here for normal distribution, we want to speak with 1 minus alpha confidence level, and what confidence level, and your confidence interval will be let's say that confidence interval is asked to be 0.99. okay, so it means that should be your 0.99. and what should your alpha be here? So you understand that your alpha should be 0.1, but since it has two tails here, do you remember from our previous lecture here? So it means that this word should be like half of these values. It should be 0.5, right? So you put these in there, minus z alpha 2 and minus plus z alpha. Okay, I just wrote them a bit badly. Z alpha 2 minus plus z alpha over 2 for the right hand side here, and I need to define the corresponding values for this purpose. So it means that you will have here up to this point, what should it be? It should be this much of area covered here, right here, for this purpose. And I need to look this up from my table, okay? Don't do any just memorizing, just rely on our table here. So what I'm curious about is like 0.495, 0.495 is where? Okay, it should be between here, right? I think I spotted it. It should be exactly between these two values, right? So it should be 2.570, 5, 15, this one. Okay, between these values, just at the middle of it, so it should be 2.575, right? Don't memorize anything, just try to use the table for this purpose. So I understand that corresponding values here, z values here should be 2.575 minus and 2.575 plus here, and the answer will be minus and plus here 2.5 times this much of standard error, and that should be minus plus 2.575 times 124. Since we have a calculator, we can easily calculate the lower limit here. Lower limit should be this much kilometers, and your upper limit should be, for the plus version, it should be 1,774 kilometers. So it means that 99% of new tests or trials like this will fall within this range. Look at this. All right, so that's it. Now two questions for you. Pause the video and try to answer them if you like. If this value has only positive values, what does this mean? Okay, look at this. If it has only positive values here for 99% confidence, so this means that, pause the video and try to answer it yourself. This means that your factory 1 is producing, you can get a conclusion like this here. So your factory 1 is producing more durable tires than the second one. You can make a comment like this. We will see this more, discuss about this more in the hypothesis testing part, but that's the idea for now. And just think that if 0 had been in this range, what can you conclude about it? Just pause the video and think about it. Suppose that your upper and lower limits would be changing between minus 300 kilometers and plus, let's say, let's say 900 kilometers. And you can conclude that 99% of your observations will fall in this range. So what can you conclude? I mean, you cannot comfortably say that the first one is better than the other one or something, because 0 is there, or so you cannot be so sure about the issue here. So that's all about the estimation of difference between two means.